Right. So section 4.3, combinations. So today we want to talk about symbol CNR. And CNR gives us the total number or total count for all the subsets of size R, size R of a given set of size n. So that's what this gives us. So we have n elements, and we are choosing only R of them. But since we said subsets and not lists, what does it mean? That the order is not important. So I wanted to illustrate here. So symbol is CNR, but there is alternative symbol that's actually well known, and that symbol is N choose R. This is how you read it. N choose R, and choose comes exactly from this description that we are choosing R object out of N. So there is a formula for CNR, and let me give you immediately that formula. That formula looks like this. You take n factorial on top. You divide by n minus r factorial. Does this look familiar? Is this the formula for P and R? Yes, that was the formula from last time, but times r factorial. So you divide even more. So that's the formula, and we'll play with that formula a lot. Although, I must admit, when we do applications or when we want to calculate quickly, there is a much shorter way to write this, but this looks kind of elegant and closed. So we will come to this formula, but just to see in some examples the reasoning why are we doing that extra dividing. So let's look at the following configuration. It's on the screen, so I'm not going to write those. I want you just to see the reason why we are doing it this way. So what's happening here? I'm looking at the set example. So this is not proof, of course. It's just an example. So I'm looking at the set with 4 elements, A, B, C, D. So here n equals 4. And suppose, so version A, I'm choosing the list of 3 elements. When I say a list, that means the order is important, do you agree? That's what we studied last time. Those are R permutations. So what was the formula? So this list would be calculated like this, P 4, 3. And generally, you don't even need to call formula. You can just use the common sense or multiplication principle. What would that be? In how many ways can I choose the first one? So here are 3 of them. In how many ways can I choose the first one? No, first one in 4 ways, because there are 4 of them. Now, when I already chose the first one, how many ways can I choose the second one? If there's no repetition? 3, and then it's how many? 2. So 4 times 3 times 2, and that's exactly which formula Formula says what? You just go n times n minus 1, n minus 2, until you cover r of them, which is what? N minus r plus 1. From here to here, there are exactly r members. But then, if you remember from last time, we wanted this as a factorial, so what did we do? We multiply by n minus r factorial, the missing ones, up and down, and that gave us the formula n factorial over n minus r factorial. That was the formula from last time. So this is just reviewing for what we did last time. What happens today? Today I want C43. What is that? I want combinations of 3 elements. That means I'm not counting the lists. I'm calculating how many different subsets. So generally, I choose 3 elements out of 4, and I don't care who was chosen first, who was chosen second. I just care who is inside, who is not inside. And the formula says, basically, what should I do here? I should do my 4 factorial in this case. And not divide only by 1 factorial, which is 4 minus 3, but I should also divide by 3 factorial. So my result will be then what? 24 over 6. I will have only 4 combinations. Why did that happen? So here on that list, I hope, is something that explains it quite clearly. Here are all 24 permutations. So here are all 24 lists. How did I list them? First row, who's in first row? Those that start with A. Do you see that? Who's in the second row? B. Those that start with B, then those that start with C, and those that start with D. Is that clear? So that's 24. But then what? I underlined 6 of them. Why did I underline them? They have the same content, although just the order is different. And should I count these 6 as 1, yes or no? Why there are 6 of them? Because those are permutations of 3 elements. If you choose 3 elements, you can shuffle them in 3 different ways. Do you agree? So that's why someone asked me a minute ago, why do we divide? Here is the reason. Because 6 count as 1. Is there another group of 6 that count as 1? Can I do it for ABD as well, yes or no? Are there 6 versions of ABD? Yes, I didn't emphasize them here. Here is ABD, ADB, BAD, BDA, DBA, and DAB. So that one also reduces 6 times, so the whole count reduces 6 times. Is that clear? So generally, that's why now we divide with extra r factorial, because those shufflings between those r chosens all count as 1. So that's why that reduces the number by the factor of r factorial. So that's the formula. And I hope it makes sense, and that's what we want to use. So, but when we calculate practically, we don't use this long formula is good when you do proofs or something abstractly, because it's kind of fairly compact looking. But if you do particular calculation, this is not how you calculate them. So example, suppose I calculate 7, choose 4. So what is this? I have 7 objects, and I need to choose 4. So in how many ways can I choose them if the order is not important? So here it is. If I do 7, choose 4, then the formula says take 7 factorial on top, take 3 factorial on the bottom, and times 4 factorial. Do you agree with me? But then what happened? This 4 factorial is also contained up there, included, and we can cancel them. So what can we do? 7 times 6 times 5 times 4 factorial over 3 times 2 times 1 times 4 factorial. So can I cancel 4 factorial? But is there then an easier way to avoid this in the future and do it quicker? So give me the rule.
N times n minus 1 times n minus 2 divided by r factorial, right?
Yes, although I must admit that I organize cancellation differently. Here's how I usually write it. Doesn't matter. So it goes like this. If I see 4 on the bottom, then I write 4 times 3 times 2 times 1. And what do I write on top? I do the same thing, but starting from 7. So 7 pairs with 4. Who's next one?
6.
Who's next one? Who's next one? 4, and I stop. So actually the way I did it, is different. To explain what's happening here, I'll do this. 7, 6, 5, 4 times 3 factorial. 4, 3, 2, 1 times 3 factorial. So n minus r factorial is canceled. Sorry. You can do either one, of course, but to explain this.
Well, the 4 is canceled too.
What's it?
The 4 is canceled.
Yes, but generally this is how I write it. And then we'll see a rule actually. Why is that? I generally like when I see starting with 4 to write 4 factorial and then whatever cancels. But there will be another shortcut in a minute. What else? I don't know if you are aware, but you can get all these calculations on calculator if you need it. So here is TID 3. How do you get that? So you go into math, and then into probability, and here are the symbols. NPR, NCR, and factorial. Unfortunately, I'm not ready for this. I have to start and say 7. Then I go into math, probability, NCR symbol, and then I say 7, NCR 4. Here it is, 35. So calculator can do combinations. Is that correct? 4 and 4 cancel. 3 times 2 is 6, so we get 35 as well. Are we okay with this? One of the main things that you need to practice doing this homework is to make sure to distinguish from your problem, are these permutations or combinations? So sometimes it's not so clear from the story which one you should call. So always ask yourself, is the order important? Two of my favorite examples that actually sound fairly similar, but give you a fairly clear message are the following ones. Suppose we have 20 students, and we need to choose, like, I don't know, president, secretary, and treasurer. So out of 20, I'm choosing 3. Would you call that permutations or combinations? Combinations. So is it important only which 3 are chosen, or also which position are they assigned to? So that means if it's important who is chosen to president, so then this will be permutation. But if I say committee of 3 is chosen, then what? Does it matter if you were chosen first or last of those 3? No, then it will be combination. So whenever there's no kind of distinction between the members of the group, those are combinations. When there is distinction, those are permutations. So let's see a few problems where we would practice a recognition in the word problem. All right. Example 4.3.2 covers some basic cases that we often see everywhere, on quizzes, exams, homework. So this is basic. Probability courses also like those problems. So here is the example 4.3.2. What does it say? Suppose that a team of 4 members is to be chosen from a group of 11 people. In how many ways can we make the team? So not everybody is in, so those will not be permutation. It will be either 4 permutations or 4, not full permutation. They are not shuffling seats. Not everybody is included, so these are our permutations or our combinations. What would you say? Combinations. Why? Because it's a team without assigned roles. So part I is what? C11-4 or 11-2 choose 4. I'm not going to calculate it because that's it. Part B. Now we are ruining the symmetry and says, suppose that 2 persons insist on working together on a team. In how many ways can we make the team? So what does it mean, insist to work together? That means either they are both chosen or none. So they cannot insist to be chosen. They said, but if you choose me, you have to choose him. So make up your mind. So what do we need to do? Yes.
Did you treat them as one then?
No, because they will be treated as 2 members. So what can we do here?
Do and and?
What's he?
Do and?
No, it's or, because you have 2 cases. So either you can design with both of them or with none. Do you agree? So let's see. No, that's the first thing. So case 1, both on the team. Case 2, both off. Agree? Now when they are both on, there's no shuffling. So what happens? If I already put both of them on, then 2 seats are already taken. So how many members do I need now?
9 choose 1, right?
9 choose 2 because we are choosing 4. 4.
okay.
So we are choosing 4. So 2 seats are already taken. The order doesn't matter, but 2 are already there. So I have a right now to choose only 2 out of how many? 9. So I have this freedom. So this would be 9 choose 2. So that's the count for committees with them. But what if they are both off? Then what happens there? All 4 seats are open, but now I don't, since I decided that they are off, so you cannot just say, oh, it doesn't matter, if they sneak in, it's fine. No, now, because you don't want to do overlap, because can I add them later on? Yes, because no committee can be in both groups. Can the same committee have them and not have them? So that's why it's important to have completely cases that that cannot happen simultaneously. So that's why here either both on or both off. There's no third case. If we follow their request, and then what would that be? 9 choose 4 because those 9 remaining. What's it?
And now we
Add them up. Yeah. So 9 choose 2 is what? 9 times 8 over 2, which is 36. 9 choose 4, 9, 7, 6, 5 over 4, 3, 2. 3 cancels. No, I lost 8. 9, up. 9, 8, 7, 6, 4, 3, 2. And then 3 and 2 give me 6, 4 gives me 2, so that's what? 126. 63 is there. Now you add them up, and the answer is what? 162. So as I said, you want somehow to break your situation into those where you can call your formulas. All right. This is whoa, what's this?
That kind of makes sense because they occupy.
No. What I did, I just, in my notes, I have to change this. It's not 9 choose 5. I'm not choosing 5. How many am I choosing? 4. So I just did. And 9, I did a problem like it's that I'm choosing 5 people. So probably I changed the text, but didn't change the solution. So if it's 9 out of 5, if I'm choosing 5 persons, then this solution is good. If I'm choosing 4, this solution on the board is good. So I'll just change the text in my notes. I'll say choose 5 and everything's okay. All right. Here's the next problem. If a club has 5 men and 4 women, how many distinct groups of 3 have have exactly one woman? And then how many teams have at least one woman? So now we have to kind of understand what these colloquial expressions mean in terms of sets and in terms of counting. So let's finish this one, and then we'll take a break. So part one. So we have what? 5 men and 4 women. So that's the total. By the way, in the notes, I didn't ask that question. But what if I ask you the following? How many committees of 3 can we make? Number of committees of 3. In this case, you don't distinguish between them. They are just members. Do you agree? So in this case, it will be what? C93 is the total number of committees without any restrictions. So 9, 8, 7, 3 times 2, which is 84, I think. 1, 3, 1, 4, 12 times 7. Yes. So there are 84 committees. Now they said the following: how many teams have exactly one woman?
5 choose 2 plus 4 choose 1? Yeah.
Plus or times?
Am I close?
You are, just one word. You said plus, he said times. So 5 choose 1, that's, 4 choose 1 is you are choosing women to be on the committee. Do you agree? Then 5 choose 2, you are choosing 2 men to be on the committee. Are these alternatives, or they are pieces of the job that should be glued together? So what did we say for those? Do I add or multiply? Multiply. I add them up. If this is like I did there, complete committees in one version, complete committees. These are not complete committees. These are stages in the process. When I choose that woman, am I done with committee or I need to keep going? That's why you are multiplying. If you have stages, you multiply, and here is the choice. So in 4 ways, you choose female part of the committee. In 2 ways, male part of the committee. Then since each of them could be combined with the other one, you multiply. So it's 4 times 10, which is 40. So out of 84 committees, 40 of them have exactly one woman. Is that clear to everybody? But then I ask, how many of them have at least one woman? What does it mean, at least one? You have one woman, or what? Or 3 women, and then you add them. Now it's or. I have complete committees with 1 woman, then complete committees with, so these are alternatives of complete committees, and I add them up. Is there a better way to count this?
Complement?
Complement. What's complement of at least 1 woman?
Only men?
Yes, exactly. So 2 use complements. Men only. Sounds like 60s clubs. So that would be what? How many candidates are considered? 5 candidates for how many spots? So that's what? 5 times 4 times 3 over 3 to 1. 3 and 3 cancels, and that would be 10. So there are 10 committees that are men only. So how many of them are the opposite from out of total of 84? That's what? 74. 74 represent the number of committees with at least 1 woman. Here it is. So you remember that idea, going for a complement can save us from calculations, because this one was much easier because then doing all these alternatives. Is everybody okay with this? So this is what you need to build doing homework and practicing for the exam, how to recognize what is appropriating and how to break this situation into situations from formulas. For example, on this one, if you don't do case 1 and case 2, you cannot call the formulas. Once you do that, you just do formulas. So you need to do formulas plus a design. Design tells you how does your configuration breaks into standard configurations. And that's not always easy. You will see going through analytic problems how sometimes this gets quite tricky. All right, let's take a break. We continue with 235.